Good morning, everybody, and I hope you had a nice coffee break. It's my great pleasure to introduce Wouter Weggelaar. Is that right? Always had difficulty with Dutch names. When we started off the FUNcube project, we got it all those years ago. I think it was about 8 or 9 years ago. We were looking around for people to do it, and we were very lucky to that Wouter volunteered, because he has lots of different hats, and his main two that concerns us is the fact that he's a member of AMSAT and a very keen and capable radio ham, but also that he works at a company called ISIS in Delft in Holland, and we have who built or assembled FUNcube U5 for us, and of course it was Wouter with his employee's hat on who did a lot of the soldering. So when we have all these Skype conferences and stuff, we have to ask him which hat he's got on. Is it an AMSAT hat, or is it as a Delft employee's hat? And I guess you've got your AMSAT hat on mainly today. Yeah, AMSAT, is that right? And BATC. And BATC, there you go. Okay, so without further introduction, Wouter, off you go. Thank you very much.
Thank you very much for the introduction, Jim. I'm still recovering a bit from a cold, so I'll try and not cough too much. My talk is going to be about the FUNcube generation of satellites, but first a bit about me. So I worked on the Delphi C3 satellite. Let me first ask you who has been at the AMSAT Colloquium before in the room, or so quite a lot, and there's also quite a lot of people that have never attended the Colloquium but are here for the convention, I guess. A bit of background. I worked on a student satellite at the Delft University of Technology in the Netherlands called Delphi C3. And as Jim already mentioned, I now work as a radio engineer at a spin-off company called ISIS, and we were called that before everything became a bit controversial with that name, but we're sticking to it. I'm also a radio amateur member of AMSAT-UK and co-founder of AMSAT Netherlands. And I'll go into detail about why in a minute. So first of all, something about CubeSats. For the people that are frequently attending the AMSAT Colloquium, this is not news. But some time ago, there was a standard devised for small satellites, because one of the difficulties of getting a satellite accepted on a rocket is basically interfacing it with that rocket. How do you keep the satellite on the rocket and eject it when ready? And for that they standardized a 10 by 10 by 10 centimeter cube that can be safely put away and stored in a container. This is a 3-unit container, so it basically can contain 10 by 10 by 30 centimeters of these satellites. And they're so-called units, and you have 1U, 2U, 3U, and it's basically just Tetris blocks. Well, not in all the weird shapes, but you can put blocks of satellites together and make multiple use. And those standard deployment mechanisms are called pods. And if I explain this with people in the room that are working for my company and I tell them it's just a box with a spring in it, they get very angry. But it is in essence a box with a spring in that pushes the satellite out, but of course in a very controlled manner. So it's a high-tech jack-in-a-box. So those CubeSats have an advantage of being cheap to launch because the interface to the rocket is standard. FUNcube, the project, a while back AMSAT-UK decided, okay, we want to also try and build a 1U CubeSat. And it was indeed financed, built and designed entirely by volunteers and supporters, and some of that work was contracted to the company that I work for, but largely the design part was done by AMSAT-UK. And after 4 years of working, it was finally launched on the 21st of November in 2013. Launched at just 988 grams, so under a kilo. Very tiny satellite. So what can you do with such a tiny satellite? So the primary mission for us is educational outreach. So this satellite sends down telemetry that is free to receive for anyone with a receiver. and the aim of that is to just go to schools and colleges and show them how to receive a satellite and look at the telemetry and check out all the interesting bits of data coming down. But there's also a secondary mission. That's basically what's in it for us as radio amateurs. There's a transponder on it which allows us to communicate. It's a single sideband capable linear transponder. So you can have a couple of QSOs going on at the same time on the transponder or CW or any other mode. That could be possible, and that's mainly during Eclipse, so when the satellite is in the darkness. And the reasoning behind that is that we expect colleges and schools to be closed when it's dark outside. That doesn't always work out, but in general that's how that works. So yeah, that's the FUNcube 1 mission, and the 1 will become important later in the talk. So some of the experiments that we have on board are different colored surfaces. So there's a black strip and a silver shiny strip of metal, of which we sense the temperatures. And one of the experiments that you can do then is just compare the two and see which one heats up quicker, which one cools down quicker in space. And then you can actually ask yourself, like, why is it doing what it's doing? And even for us as radio amateurs, sometimes the results are quite interesting, and you have to really think about it, like what is happening exactly. And then the structure itself has these corners that are, in this case, black on one side and silver on the other side, and there's some protective tape on this side as well that we took off prior to launch. So that's one of the experiments, only one of the experiments, but there's many channels of telemetry to look at: battery voltages, sun sensors, temperatures, of course, very interesting to look at. So we have the data available. All the data is available from the data warehouse, the FUNcube data warehouse, that is done by Dave Johnson here on the front row. So all the data flows into this warehouse and is freely available. You can download CSV snapshots of the data or Excel files, or have a look at it online and browse the data, look at the graphs. So yeah, there's quite a lot of interesting things, and it is just interesting to look at it and try to see if you can reason yourself through all these graphs and what's happening. For instance, here you can see silver panel is the red line and the black panel is the green line. You can already see that there's a difference there in temperature, but also the rate of cooling and heating is different. So those kinds of things you can spot and explain, but for kids it's nice to also think about this and see if you can come up with that explanation. Yeah, as I said, it's all available online on the warehouse. Now to the hardware bits. So the satellite contains a couple of CubeSat boards, which are these 10 by 10 centimeter boards with some predefined hole pattern and a connector, which you can stack on top of each other to create your electronics. And this is the CCT board, command, control and telemetry board, which is basically containing a microcontroller, the MCU, and a CPLD, which is, so this is the microcontroller, and there's also a CPLD, a programmable device that is supervising the microcontroller. So if for whatever reason the software should crash on the microcontroller, then the CPLD is monitoring that and resetting it. And the CPLD also has a sort of backdoor commanding interpreter, so we can switch off the microcontroller and reboot it. So if anyone in the team goes, have you tried turning it off and on again, then we can with this device. Then a radio. Of course we need a radio. So this is my design. It's what we call a UV transceiver, UHF, VHF. So the uplink is on 70 centimeters, downlink on 2 meters, and it has the transponder on it and all the electronics needed for the command receiver, the telemetry downlink, and the transponder. Some of the people that are frequently tinkering with hardware might recognize some parts. It's really classic electronics. There's not so much special about this board. Obviously, it's designed for the environment of space, but some of the filters. This is, for instance, a Murata 10.7 megahertz filter, which is also in commercial transceivers. a helical filter here, over here for the output. Motorola FM receiver chip, which was used in cell phones and a lot of broadband FM equipment. So yeah, there's all kinds of traditional electronics in there, and we're already moving to further generations. But yeah, we started with this design. And the output of that board is going to the PA board, made by David Bowman. I don't know if he's in the room, he's probably. And that's basically just a power amplifier, and power in this case is not more than half a watt, even a bit less on FUNcube 1. So yeah, but it is made to be very robust, and it turns out to be very robust indeed. Also very classic design with one FET, and yeah, works really well. So then you put the hardware in a stack frame. Basically start stacking in also batteries and some other things. Put it in one of these 10 by 10 by 10 standardized CubeSat frames. And that's basically then ready to go. Well, you have to stick on some solar panels, otherwise it will be a short mission, and some aerials. So the aerials are basically the sort of springy tape measure type aerials. This is shape memory alloy, but so it's a slightly more fancy variant, but in essence it's the same as tape measure. And they spring out of the bottom, and then some solar panels on all sides to generate the necessary power. So this is 10 by 10 by 10 centimeters in size, and the amount of energy that you can expend on such a system is around 2 watts, slightly less than 2 watts of DC power coming in from those solar panels. I'm from the Netherlands, and there I always tell people this is the same as the front light of a bike, because everybody knows what a bike light looks like in the Netherlands, but it is only the headlight of a bike in DC energy, and we're doing DX with that. All right, so you need to receive such a satellite. So in the project we also developed a dongle, a USB receiver, done by Howard, G6 LVB. I think the dongle is now quite famous, but when we started this, Howard was not present at a certain meeting, and then everybody decided, well, he's not here anyway, so let's give him the ground segment. We all want to work on the satellite, so we'll just give him the ground segment. And well, Howard went away, didn't hear from him for half a year. I think he just disappeared, and then after a while I said, I got it, and then that was the dongle. And then I think we thought we had to produce 500 or something, and that would be enough forever.
He reckoned 50 to start.
50, yes, but we talked him up to 500, and I don't know how many we sold now. But and with the purchase of a dongle, you're also supporting the project. So a part of the purchasing price is donated towards AMSAT. So yeah, that is a sensation in its own. But yeah, that dongle works really well for receiving the satellite, and was designed to that. So yeah, then you're done with the satellite, you're done with the ground segment, you have something to receive it, and then you have to say goodbye to your satellite and basically bolt it on a rocket. Well, first we needed to get it to Russia, and what do you do if you want to get your tiny satellite to Russia? You rent an Antonov plane. That happened to go there with some bigger satellites. The satellites were collected by that plane from all the countries that were launching satellites from that launch, and they were basically flying around with this Antonov around the planet to collect all the satellites, and we were there with like one tiny case, like there you go. In reality, there were more CubeSats on this launch, so there were slightly bigger cases. But and here's the team in Russia with these two deployers. Those are the springy boxes, charging the satellites and then waving goodbye to them. So I don't know how many of you have been to Bletchley Park, which is quite close to here. I would highly recommend a visit if you're here anyway. So we were lucky enough to be able to use the National Radio Center that is over there to use as our command station. So we were able to set up there, and here you can see how that normally looks and how it looks now as well, I think. Well, maybe they've put up a screen. or something more. By the time we were there, we added, I think, about 20 screens, because we needed more screens and more radios and more people. So yeah, at launch day we were there, watching all the telemetry and all the sending all the commands. And then on the November 21st, we had success, and then yeah, the real work starts. You now have a satellite in orbit, and what do we do with it? But at the same time, yeah, we were already getting some outreach done, because the whole idea was to go to schools and talk to people about STEM subjects, science, mainly satellites and radio. And the same day we actually got a request from, I think it was the BBC, asking us like, oh, we actually phoned the school, they have time now, can you just go and do this demo? And that was 2 hours after lunch, I think. So 2 hours after lunch, Kieran here was standing in a classroom explaining things about the satellite that we have just launched. And yeah, we now have had a product to sell, so we're getting all kinds of nice reactions from all over the world, also from teachers that were using FUNcube in the classroom. So yeah, data recovery. So we're transmitting all the time. So FUNcube is always transmitting telemetry. It's never quiet, which is a really good thing if you're looking into outreach, because you don't want to be uncertain about the signal. Like, the signal should just be there. So yeah, we're always transmitting, and therefore also over oceans and places where we don't have ground stations. But we have a quite nice network of ground stations around, which is basically you guys. Radio amateurs putting up a ground station or listening to it with our software and forwarding the data to Dave, to the warehouse. And I had a look this morning, and FUNcube has broadcast since launch roughly 6.3 gigabytes of data, and this is 1200 bits per second. So in its lifetime, it's now transmitted 6.3 gig, and of that we recovered 1.4 gigabyte, which is 20%, more than 20% of all the data. And imagine not having ground stations on the poles or large bodies of water. That's actually quite impressive. And out of that, we even recovered for whole orbit data, which is basically a buffer that builds up over time. We recovered 83% of all the data that was transmitted as whole orbit data. So we have 83% of the history of this satellite in the database, and that's done by us, by radio amateurs, which makes a lot of agencies really jealous. So you get some data down. This is, for instance, high resolution sensor data from the sun sensors. So you can basically see the spin of the satellite here. So the sun sensors are plateauing on the top. That's actually saturation of the analog to digital converter. But yeah, you can clearly see that it's going in the dark and then moving into the sun again. So from this you can actually deduce the spin rate, and you can also just look at like the orientation changes of the satellite. And we have a guy in Australia that is doing this on a daily basis, and he's just by hand checking how long it takes for these dips and writing this down in an Excel and sending us updates, which is really great.
Colin.
Yeah, Colin. And so, Colin, if you're watching, thank you. He's really also taking care in finding people to do it for him if he goes on holiday. So he's really like every day we get this data from him, which is great. And we didn't ask for that. He just said like, okay, I'm doing this. I like to do this. The amount of active users per day. So I've plotted since launch what has happened with the amount of users that are submitting data. So launch day, you can see there's a huge spike of interest. Everybody wants to receive it. And then a lot of people go like, okay, done that, check, next. But there's actually quite a lot of people, and this is 100, this line. So there's more than 100 people on a daily basis that are still submitting data. And that's quite constant. Sometimes you see the lower and higher peaks, which are basically weekends or weekdays or days and nights. So there's a bit of fluctuation there, which is why it's a band. And what you can also see here, and this is data for only FUNcube 1, is that there's a spike of interest again. This is when Naive was launched, and I'll come back to that later. This is another satellite. And people were listening to this other satellite, but also thought like, oh, I can also pick up FUNcube. So let's do that. So we got another spike of interest there because people were using the same software. This plot shows a cycle. This is the solar panel input voltage. And the green one is the solar panel current, and the one underneath that is the bus current, so the energy taken out of the batteries or solar panels. And I am intrigued by this plot because what it's showing is that overall the amount of energy that we get from the solar panels is increasing. And normally solar panels tend to degrade in space because of radiation and UV, but our solar panels are starting to generate more power. And I actually don't know why. This might be an influence of the spin rate of the satellite changing, and then the maximum power point trackers that are taking the energy out of the solar panels being more efficient with that specific spin rate. But I actually don't know for sure what that is. So if anybody has any bright ideas why we're producing more power. And we can also see a nice yearly cycle here, which is basically just the illumination conditions of the satellite. So yeah, we will continue to watch this with great interest, see how that develops. Maybe at the end we will have enough power for more downlink. We can't, but... And then you can also look at other interesting things like solar eclipses, not the one in the US, because we happen to not fly through the eclipse zone in time. But this was an earlier one where we had basically current from the panels, from the solar panels going into the system, then a drop, basically when it went into the darkness, then nothing, then went back up, like, oh, I'm in sunlight again, and then for whatever reason, hey, it dipped down again. And this is actually flying through an eclipse. So you can see the current going down, almost total eclipse, and then back up. So yeah, you can detect eclipses from spacecraft. And I think AMSAT-US has done a similar thing with the Fox satellites. They can also see the eclipse happening. Right, I was mentioning this warehouse, data warehouse. There's not a competition going on between people that are trying to get to number one. The reason there's no competition is that Mike Willis is by far on top of this list. Are you here, Mike? No, he's not here. Well, he's around. Yeah, so he's basically submitting a lot of data. We want to know his secret, but I'm pretty sure he's not going to tell us. And then next to it is PB0AHX from Delft, who's a friend of mine, living quite close in my area. And I basically told him a lot of information about this satellite when I was building it. And he's one of the other people that like religiously tracks and sends data. But there's a couple of other people that are from my area that are actually competing to get higher in the scores. But yeah, also a lot of people that just follow the satellite and are sending the data on a daily basis. So thank you. I mentioned Delphi C3. That's the satellite that I started working on. And on Delphi C3 we started making a distributed ground segment, which basically means we get data from other people into a central database, and we collect this data to get more telemetry in our database. So we did that for Delphi C3, and we also did that for FUNcube, and there's now more and more systems starting to do this. So I compared the two systems and actually was interested in how many active users you get compared to registered users. And it's actually quite similar. So in both cases, about half the people actually have a useful contribution to this data gathering. So that's actually really nice. And again, this makes agencies jealous because this doesn't cost any money or not a lot of money apart from the hosting of the servers. But that's volunteers basically putting data in the database. Yeah, so that's definitely all really good news. I don't know, Dave, I haven't checked the latest. These are old numbers. So if you can check, then maybe next year we'll have an update of that slide. Yeah, so as I was mentioning earlier that we have some other missions going on, and that was part 2 of this talk, the ongoing developments. So FUNcube was just the start. We launched FUNcube. We thought, okay, let's build a 1U CubeSat. But while we were building, we were already getting people saying, okay, we have maybe a spot for you, or maybe you can deliver us some transponder boards, or can you help us with things? So we really found that there was a need for people to have communication systems, to have a redundant backup system or STEM outreach in their missions. So yeah, during construction of FUNcube 1, we already identified a couple. And this is the current family of satellites that we're working on. So after FUNcube 1, we got FUNcube 2 on UCube 1, FUNcube 3 on QB50 P1, and I'll go into detail on each of them. FUNcube 4 and SAO, we are at the talk of Chris Bridges was talking about SAO yesterday. FUNcube 5 on Naive 1, and then FUNcube 6 on JWA1 and maybe more to follow. So that's our family tree, or yeah, all we've got. So this is FUNcube 1. Notice that FUNcube 1 looks very similar to Naive, looks very similar to JWA1, because they're almost identical. So those are basically close family. Then we have a 2U satellite. So these are 2 of those cubes on top of each other, called QB50 P1. This is UCube, which is a 3-unit satellite. And this is a rendering of SAO. And I don't know, Graham, is there any newer one than that? Because I think everybody's been using that one.
Hasn't changed.
Yeah. So yeah.
SAO is like 3 units, or is it like?
No, SAO is actually not a CubeSat. So
Not a CubeSat.
SAO is what they call microsatellite, but it does contain similar systems. So yeah, the downlink will be compatible with what we are doing, and so we're still calling it FUNcube, although it's not a CubeSat. So yeah, first of all, we had FUNcube 2 on UCube 1, which is the first UK Space Agency satellite CubeSat, and contains the CCT, RF and PA boards, and runs telemetry and a transponder. I don't know about the current status of UCube, but it's still operational for us. Like the FUNcube system is on. Graham, do you know if it's on telemetry or on transponder?
It's on 24/7 transponder with low power telemetry.
Yeah, yeah. So there is basically, it is continually transmitting, and it is transponder is on, and when the transponder comes on, the telemetry drops down 10 dB. So the telemetry is always there, but it's less power. And that is end of mission for the UK Space Agency. They've achieved everything they wanted with the satellite, and now we can basically enjoy the transponder. So for the UCube mission, the aims were to have a redundant communication system for the UCube satellite, provide the telemetry beacon for the STEM outreach, and for us have an extra transponder in space, and then establish a data warehouse similar to FUNcube 1's. Has its own transmitter and receivers on the satellite with its own aerials as well, and can be controlled by the onboard computer of UCube, the NanoMines. So when it's in redundant comms mode, we transmit some of their data down as well. Interconnection is via I2C bus, and it needs basically power from their satellite bus, and when that's on, we basically are on, and we can operate. And yeah, there's a separate warehouse for that as well, also done by Dave. QB50 is basically another project that we got involved in. They needed to launch precursor satellites. What they wanted to do is de-risk the main mission. So QB50 is a constellation of a lot of satellites made by various institutions and universities. And to de-risk a couple of elements in this mission, they wanted precursor satellites, basically testing out some of the things like sensor units, avionics, to see if the concept was feasible. So they built a couple of precursor satellites and invited us to put the FUNcube system in one of these satellites, with the exception that we could not fly a CCT board, we only could fly the RF MPA boards, which means that we don't have telemetry on the satellite, but we have a transponder. And that transponder is currently working on a timer. So it is on and off by timing, and that's because of power budget. So if it would be on all the time, the batteries would rapidly drain and the satellite would become power negative. But it is available for use. FUNcube 4 on SAO, I'll be quick on this one because there was a talk yesterday by Chris Bridges. It's an ESA project, has been running for, well, a long time. I think we started in 1999 with the original design, so it's been going for a long time. But it will also have a FUNcube compatible telemetry system, and it will have L-band as an uplink, so there will be a new opportunity there for all the L-band gear that people might still have or are maybe going to build. So this will have an L-band uplink and a 2-meter downlink. So L-band is 23 centimeters as an uplink, FM, and a downlink on 2 meters. So that's a new exciting thing to look out for. And FUNcube 5 on Naive, I will go a bit more into detail about this one because it has recently been launched and become operational. So that's the first time that somebody came to us and said, like, we want a FUNcube. We just want what you did with FUNcube 1. Can we just have a copy of it? So we said, well, maybe not, but we'll actually help you build one. So yeah, I see that some of the text is out of the off the screen. But yeah, a Naive satellite has been built by the Mohammed bin Rashid Space Center in the UAE, the Emirates. And they have been doing that in cooperation with a university, and their students needed to get hands-on experience with a satellite. So AMSAT-UK has provided, again, these 3 boards, the CCT board, RF board, and PA board. And my company ISIS has built the rest around it, then went with the parts to Dubai and had them assemble and test all the parts. And yeah, that was FUNcube 5, so that looks very similar to the original FUNcube. Launched on a PSLV from India in February 2017, so that was that spike that you saw earlier in the plot of people listening to the satellite. This satellite was launched, and right after that, all the people were like, oh yeah, we also still have FUNcube. Let's also listen to that again. Yeah, deployment. So this was the first time for me that one of the satellites that I worked on was being filmed while being ejected into space. So what you can see here in the top corner is Naive and Al-Farabi, another satellite. They were sharing one of these tubes with the springs. So those tubes are 3 units in size. So you could put a 1 unit and a 2 unit behind each other and eject them at the same time. So Naive is up front, and then Al-Farabi is a 2 unit behind it. And this has to be very carefully calculated because you want the satellites to not crash into each other after they're ejected. So there's quite a lot of planning that goes into finding out which satellite goes where and what time they release them so they don't bump into anything else. And this launch had more than 100 CubeSats on it. So in the end, this video also has quite a lot of other satellites in it. But yeah, I managed to grab one frame where you see these satellites popping out. Differences between what we had for FUNcube and the next generation satellites is basically the addition of an IMTQ. So all the other boards were all in there before. So on top you have the antenna system, then a CCT board, which is the command, control and telemetry board. We were shy to use the word onboard computer because we thought that was not really a nice way of describing the board, because it's not really a computer, it's much simpler than that. So yeah, CCT board, an RF board for the communication, the PA board, like I said before, to amplify the signal, then an EPS, electronic power system, basically the batteries and the power converters, and an IGIS on the bottom, which is an interface system, and then the new addition is an IMTQ, and that's a magnetic torquer system, which has coils in all axes, which can be energized to basically move the satellite and to align it with the Earth magnetic field. So you can basically change the orientation of the satellite. What we're doing with that is actually not really tracking the orientation, but we're trying to slow down the movement of the satellite. And in FUNcube that was passive with magnets and hysteresis rods, and now it's active. So that was a request of the customer. They wanted to play with this system. Then we had some updates on the hardware, extra memory on the computer, a readout for the sun sensors and a readout for the temperatures. That used to be a different board, and we now integrated that into one. On the RF board, much better frequency stability and wider transponder filtering. The frequency stability was one of the things that a lot of people noticed, like the FUNcube 1 signal is not always stable. It changes quite a lot with temperature. And that got solved in this. And then testing commences. This is what you call flat set. Well, it's not very flat, but at least you start stacking boards up and start measuring things. And then it's testing, and more testing. So this was basically I think it was more of a showdown than a test session. It was like, let's see who can build the biggest tower of equipment in the office. Yeah, I wanted to do a lot of tests. We basically have these testing weekends over in Delft, where some of the AMSAT-UK people also come over to test. And then we try to get as much done at the same time as possible. So while I am doing RF testing, there might be software engineers changing other things. And that also means that sometimes when I'm testing, for instance, the output power, all of a sudden my signal disappears. And I have to sort of tell the software engineer, like, could you not pre-program it now, please? But yeah, this is a really good way with the team to get together and actually get stuff done. And then, yeah, that tends to look like this. Then on to Dubai, in the clean room, basically building the satellite over there and teaching the students over there. Also setting up the ground station to track the satellite from the university. And yeah, it was a really nice experience. Again, upload ranking. Also, this satellite has a warehouse. And here you can see the same Dutch people trying to be on the top, which, well, I think they have a chance here. Mike Willis is not, no, he's actually not on there at all. I don't know why there's a gray square there. Okay. The latest incarnation is JY1sat, Jordanian's first CubeSat satellite, or first satellite in general. So Jordan was basically also looking for such a mission. I'm not sure if they've just looked to Dubai and went like, one of them, please. But yeah, they want some different things entirely again, because yeah, everybody needs their own touch on the mission. So we've added some features on their request, which were also in line with what we wanted to do. So you have SSDV, slow scan digital video. Some of the people that are doing high altitude balloons might know the system. It's basically a digital variant of SSTV, which basically builds up the image gradually and also is able to fill in blanks if you get more data later. So the CCT board has again been upgraded with more RAM to hold these images, because we don't have enough memory to store those images, and now we do. And the RF board is getting small upgrades again to make it even more stable. There's some oscillators being changed again. So that's the image of JY1sat. This is a week ago, and I think it's currently, it might be in a case going towards Jordan. So I hope that soon we will have yet another, well, that sounds a bit bad, yet another FUNcube, but yeah, we're counting. So in essence, we have now a family of satellites. We have already 3 or 4 generations. So there was a line through that one. I think the export messed up some of the formatting. So generation 1, FUNcube 1 to 3 were pretty much the same boards. Then the second generation, we added stable oscillators. That's FUNcube 5 or Naive 1. Then I basically split generation 3A and B because we're working in parallel on those. FUNcube 6, which is the Jordanian J1 set, adds an image downlink capability. And 3B is FUNcube 4 or SEO, adds many other things like faster downlink, CAN bus, the L-band uplink, and many more. And that was the topic of the talk of Chris Bridges yesterday. If you missed that, the talk is going to be on the AMSAT-UK YouTube channel soon. So you could rewatch that over there. So where is this all going? We have a proven ground network. We have quite a lot of people feeding data. We have a proven telemetry format. So we have a very robust way of communicating. We are going to be downlinking images from J1 set. We can go faster with the SEO hardware. And the last question is, what do you think we should add next? Because frankly, we are waiting for inputs because we can keep building these, but it might be nice to add something new in the next generation. Thanks for your attention. Any questions?
Thank you very much.
Yep.
I just want to make one comment, it's not really a question. What Wouter didn't mention is that the next generation of FUNcubes that we've done, like Naive and stuff like that, we've sort of invested a lot of intellectual property in the FUNcube design, and the people like Jordan don't actually get it for free. We get a bit of a kickback in terms of a little bit of finance, not a huge amount, but it helps pay the insurance for the satellites, but also in components and things like that. So we're building up a store ready for our own satellite, which is a little bit in the future, but may come along. Sorry, I hope you don't mind my mentioning that. So questions? Okay.
Yeah, very interesting, thanks. What is the cost of launch?
That is a both easy and difficult question because launch costs are changing rapidly at the moment. So the cost of launch when we were doing the FUNcube project were about £50,000 per kilo, and we were 1 kilo, so that's about it. But that has gone up quite rapidly, and that's basically because there's a high demand on these launches. Current going prices, I'm not sure, but I think it's more than double at the moment.
Thank you. Anyone else?
More sort of a comment and also a request. You know, there's quite amount of data coming down and sitting down in the warehouse. And we from AMSAT SA are looking at analyzing this data in some larger fashion, doing some statistical analysis on it and trend analysis. Now, we'd just like to know if anybody else would be interested to contact us so we can be a larger group doing this type of thing and just not plotting the data, but getting some useful, real information from this data. Thank you.
Yeah, that's actually a very good comment because we welcome people to analyze the data. The data is there and it's not a secret, it's out there. If you want the data, contact us, mainly Dave or me. And indeed, if there's going to be analysis, let's work together. Let's look at the data together. So yes, it's a very good comment. Please get in touch if anyone wants to have a go at it. There's quite a lot of hidden secrets in there.
Is it large down there?
Yeah. Oh yes, it is a quite large file.
Well, any other questions?
What's your current estimate now of the life on the satellites? Now they've been up there, one's been up for a while. How much more life do you reckon on it?
Yeah, so the question was, what is the life estimate of the satellites now that they've been up there? That's a really difficult question to answer because the expectation is in general, does it survive the launch? Does it survive the first month? Then you can last for tens of years. But there is a certain statistical probability that something will just go wrong and it will fail, and that's mainly due to radiation effects. But other degradation, like slowly deteriorating solar panels or batteries running out or those kinds of things, can take very long time. So in my experience, for instance, in Delphi C3, that is still working. FUNcube was launched in 2013, still working. UCube, the FUNcube subsystem is still on there and working. QB50 is still working. So all of them so far that have been successful are also still working. But we do see quite a lot of satellites that go up there and either have an instant failure, so there's either a design problem or something that on the way goes wrong, or they have the first month and they are just unlucky and get a certain event on board that kills them. If they survive the first couple of months, then usually it is whatever gives first.
So you don't have a sort of thing for the engineering bathtub, you know, initial failures?
Yeah.
I've got no idea.
Yeah, so the question is there an engineering bathtub curve to this? There has been, but that was largely by all the pioneering satellites in the past. And a lot of this knowledge is all shared and open. All the papers are open, so you can learn from other people's mistakes. So yeah, quite a lot of it has already been found out about in past missions. So at the moment, it is quite reliable, I would say. But that depends on if you get to build a satellite for the first time or if you've done it before.
Thanks, Wouter. Any final questions?
Yep.
Just a quick one. Do we have any idea of a launch date for JYSat-1?
A date I can't tell you exactly, but it's first quarter of next year. But notoriously launches slip. So, but yeah, currently Q1 2018. Yeah.
Okay, I can't see any more hands, so we'll call that a wrap. Wouter, thank you very much indeed,
Yeah,
and
you're welcome.
good luck with the next launch.
Yeah.
Thanks very much.
Thanks.
Next presentation here in about 10 minutes or so.